Now, in our last video, we saw how to connect the ammeter and the voltmeter to your circuit. Now, in this video, I'd like you to notice that current and voltage are in phase when it comes to a pure resistive circuit. So this one is a pure resistive circuit. Can you see that it's only the resistor that is connected? This one is pure capacitive, and this one is pure inductive. So here, look at the graph of voltage and then take a look at the one of current. Can you see they rise at the same time, hit the peak or maximum at the same time, reach zero at the same time, minimum at the same time, and then back to zero, like that. So they are in step, or you say they are in phase. Now when it comes to these other ones, capacitive and inductive, they are out of phase. So take a look at this one. I think I should remove this guy so we see clearly. All right, so you notice that they are in phase. Current rises first and then voltage follows. It's as if voltage is chasing after current. Can you notice that? Okay, now same here. But if you don't want to model it up in an exam, remember that for an inductor is just a coil. All right, so because the current is varying, is changing, is alternating, there will be self-inductance. That is, EMF will be induced in the coil. And you remember Lenz's law. It will position itself in such a way as to oppose the current that is giving rise to it. So current is always pushed back, all right, in an inductor. So because of that, current is lagging, is always lagging. So current leads voltage in a capacitive circuit, whereas it lacks voltage in an inductive circuit. I hope you understood that. All right. So there are about 5 points that I'd like you to take note of with respect to each of them. So for a pure resistive circuit, point number 1. Okay, point number 1. Now, the opposition to the flow of current introduced to the circuit by this guy, the resistor, all right, is R. That's resistance. And the unit is the ohms. Okay, point number 2. When it comes to a pure resistive circuit, current and voltage are in phase. Okay, and that means that the phase angle is 0. The angle between them, between current and voltage, is 0. All right, excuse me. The third one is the Phasor diagram. Now, a phasor is just a rotating vector which we use to represent any of the AC quantities, whether current or voltage. So if I start with current first, it usually takes the positive x-axis, all right, which is the current. So if this is the current, that means voltage will be like this. Voltage is usually bigger in terms of magnitude. So can you see they are pointing in the same direction? The angle between them is 0. So this is the way you represent them phasor-wise. Now, point number 4 is the graphical representation. So if this is the voltage, let's say this is voltage, so how will current be? Current will be smaller. It will also start at the same point. So you see the peak, get here, the same peak, and then back to 0. So they started at the same time, hit the peak at the same time, 0, and then the minimum at the same time, back to 0, like that. So this is how you represent current and voltage graphically. Now the 5th point is that Ohm's law still applies here. V is equal to IR, all right? Of course, if you're talking about V naught, it should also be I naught R. If you're talking about V RMS, it should also be I RMS times R. Is that okay? Now, two vibrating systems of the same frequency are said to be in phase if their maximum, 0, and minimum values occur at the same. Of course, we've noted that. Now, I didn't mention this. We have already covered this. We've covered this. Please watch the videos before watching this one. This is where we are right now. And then I've also covered about 30 questions with respect to AC. All right. Okay, so if we also come to a pure capacitive circuit, the same point number one, the opposition to the flow of current introduced by this guy, the capacitor, is known as capacitive reactance, and the unit is still the ohms, just like resistor or resistance. All right. Okay, and its value, capacitive reactance, is equal to 1 all over omega c. All right, and if omega is 2 pi f, we can write it like this: 1 over 2 pi f c. Is that okay? All right, now, but I need you to notice that capacitive reactance is inversely proportional to the frequency, and is also inversely proportional to the capacitance. All right, so if I want the opposition to the flow of current offered by a capacitor to decrease, if I want it to decrease, that means I have to increase the frequency. All right, or increase the value of the capacitor. Is that okay? Very important. So look at this question. Of course, the unit of XC is ohms. Don't forget that. Now, if I'm to represent this graphically, let's say the graph of, sometimes they ask it in the exam, graph of XC, capacitive reactance, against the frequency. Okay, since the relationship is inverse proportionality relationship, the graph will be like this. You remember? Okay, for direct proportionality, it will be straight like this. Okay, take note of that. Now, point number two is that current and voltage are out of phase. Out of phase. Okay, now the angle is minus 90 degrees. So it's angle of lead. Current is leading voltage. If you have angle of lead, it's negative. If you have angle of lag, it is positive. Please don't model them up. It's very important. Okay. Now, point number three is the phasor diagram. So if current being the reference quantity assumes the x-axis, positive x-axis, since it's leading, and we are going like this in anti-clockwise manner, so voltage will be like this, and the angle here is 90 degrees, or pi over 2 radian. Okay, so current is leading when it comes to a pure capacitive circuit. All right, point number 5 is the graphical representation. Okay, so how do you represent them graphically? If this is my graph and this is my voltage, for instance, this is my voltage. So current, since current is leading, current will start here, something like this. Okay. All right. Notice that when voltage is still zero, current is already at this point. So current is leading. There's also another way you can represent it, but this is okay. Now, finally, the Ohm's law still applies here. All right. That's point number 5. V is equal to I, but instead of R, because the opposition it introduces is XL. So this is how you write it. Remember, if you're dealing with peak, be consistent to be peak XL. If it is RMS, to the V RMS is equal to I RMS XL, like that. Is that okay? Now look at this question here. In an AC circuit that contains only a capacitor, the current is what? Current leads voltage. So option D is the correct option. All right, so let's answer this other one. At what frequency would a capacitor of 2.5 microfarad used in a radio resistor have a reactance of 250 ohms? Okay. Right, so I know that capacitive reactance is equal to 1 all over 2 pi fc, right? So since I'm looking for the frequency, let's make f the subject of the formula. Okay, so if I cross multiply, I will have that XC, okay, times 2 pi FC is equal to 1. Okay, that means F, which is what I'm looking for, F will be equal to 1 all over 2 pi times C times XC, like this. So if I'm to plug in the values, I will have 1 all over 2 times pi times, okay, the capacitance is 2.5. So 2.5 times 10 raised to the power minus 6, then times the capacitive reactance is 250. So 250, like this. All right. Now, if you have your calculator, you can quickly punch, but let me show you how to solve without using calculator. So this will be F is equal to 1 all over, I have 2 times pi times, this will be 2.5 times 250. Now I'm moving this 10 raised to the power negative 6. So 10 raised to the power negative 6, if it comes up, it will become 10 raised to the power 6. You remove the negative sign. I hope you know that trick. Okay, so at this point, I can move this decimal point to the front so that this becomes 25, and then I increase this one to 7. Hope you remember that trick. Okay, so now if I do that and then I cancel, okay, I cancel this, or let me leave this, let me rewrite it, then I have 7 over, then these two will multiply 250. Okay, so I have pi times 25 now times 500. I hope you can understand that. So this is 10. What did I do? This is 10 raised to power 7. Okay. So now I can cancel if I want. Okay. Cancel 0, and then cancel 2 zeros here, up here, so that this one becomes what? This becomes 10 raised to power 5. I hope you can understand that. Okay, so we have this is 100,000 all over pi times 25 times 5. So 25 into here will give us 4. So this is 4,000 divided by 5 here, 1. 5 into 4 to give us 8. So it's 800 over pi. Just take your time and solve. You will get 800 over pi hex. So the correct option is option C. Okay. All right. So this is where we are going to end this video. All right. For a pure inductive circuit, point number 1, the same thing. The opposition to the flow of current introduced by this guy, that is the inductor, is inductive reactance, like this. And the unit is also ohms. Remember, whether reactance, resistance, or impedance, the unit is ohms. And then the formula is like this. XL is equal to omega L. Since omega is 2 pi F, yes, we can write it like this. Okay, so notice here also that this guy and the frequency are directly proportional. That means the graph will look like this. The graph of XL against F will be like this. Okay, so if the inductive reactance increases, the frequency will also increase. If it decreases, the frequency will also decrease, because they are directly proportional. Is that okay? All right, point number 2, they are out of phase. Current and voltage are out of phase, and the angle is plus 90. Remember, angle of lag, that means current is lagging. For a capacitive circuit, angle is leading it, and it's negative. All right. Okay. Point number 3 is that current is lagging. That means voltage is leading. So if we draw current, usually you start with current as the reference phasor. Current is this, and then voltage will now be up like this. the angle is still 90 degrees, or pi over 2 radian. Okay, so that's the Phasor representation. Number 4 is the graphical representation. Point number 4. So this is the graph. If this is our current, so that means voltage voltage is bigger, but it will start. Okay, so current is still at this point, voltage is already here. Can you see? So voltage is leading. All right, and then finally, remember that Ohm's law is still applicable here. So V is equal to I times XL. Remember, if it is V naught, make sure you are consistent. I naught and then XL, and then like that. So this question here says, show the graph of XL against F. I've already shown that. And then here, you notice that current is lagging. So the correct option is C. Current lags behind voltage by 90 degrees. So this question says, at what frequency would a 10 Henry inductor have a reactance of 2000 ohms? Okay. All right. So the same thing, you take note of the formula. Inductive reactance is XL is equal to omega C, which is, let's write in terms of frequency, 2 pi F. Come, what am I writing? This is L, sorry. L, 2 pi F L. Okay, now we are looking for frequency, so we make F the subject of the formula. So F will be equal to X L over 2 pi L. I hope it's clear. So if we are to plug in our values, we have F is equal to XL is, that's the reactance, 2000. So 2000 over 2 pi times L is 10 Henry. Okay, so 0 takes care of 0 here, and then 2 here. So we have 100. So it's 100 over pi hex. That's the correct option.